Well, arithmetically, we would just be adding 3, add 3, add 3, Q. That is arithmetic, which will give us a sub n equals the first number plus n minus 1 times our common difference, which we can reduce down to 3n. 7 minus 3 would be plus 4. It was a good idea to just double check. My third term should be 13. 3 times 3 is 9, plus the 4 is 13. Okay, that's good. Now, for a recursive, it's an easy one to forget. Just remember, recursive uses that term and term before. And for arithmetic, it's the term I want equals the term before it plus our common difference. So to write that arithmetically, I do have to start off by saying, hey, my first term is 7. Now, the term I want equals the term right before it plus our common difference of 3. That is my recursive. And both those should work out. All right, let's go over homework questions, because I'm sure we got some. Yeah, Labib. So that it had an answer? Yeah. So all of these would not be... Remember, yesterday we talked about that these aren't necessarily arithmetic or geometric. We're just using those ideas to come up with equations for it. So neither isn't going to be a good answer on like a test if I say find the explicit formula. You will actually have to find one. This one is probably the harder one out of all of them, just because you have to look for a pattern before you can see a pattern. So it looks way off the rails at first. It looks like Mr. Pabian made a mistake in the writing it, because we have all of this stuff. Now, it looks like nothing. I mean, our numerator is 7, 5, 13, 18. Our denominator is 4, 4, 16, and 16. So the problem with that is I need to have some kind of pattern in the denominator. I need some kind of pattern in the numerator. If we make all of our denominator 16, that also doesn't work. Now, this is what's so weird about this one is I want to create a pattern with our denominators. So I can turn 2 into 4 over 2. 7 over 4 I'm going to leave as 7 over 4. But 5 over 4, I'm actually going to double that to make it 10 over 8. Then I have 13 over 16. I'm going to double this one, and I'm going to have 16 over 32. Now I can see on the top, I have a pattern where I'm adding 3. On the bottom, it looks like I'm multiplying by 2. So we have an arithmetic sequence on top, plus 3, plus 3. On the bottom, we're going to have geometric because we're multiplying by 2. So that means our end answer is actually going to have an arithmetic on top. For arithmetic, you take your first number, which would be 4, plus n minus 1 times your common difference, which is 3. On the bottom, you're going to have a geometric, which is your first term, times 2 to the n minus 1. Now, this is actually a really good problem to do this because I can simplify this. This is going to get to your question, too. So if you look at that 2 times 2 to the n minus 1, you can simplify. On a test, I'm okay with this answer. All right, I would prefer you to simplify at least the top one, but the bottom one, I'm okay with 2 times 2 to the n minus 1. But let's talk about how we can simplify this. And I want to think about this as being 2 to the first times 2 to the n minus 1. Now, I'm going to show you a power rule. If you have x squared times x to the 5th, when you are multiplying things that have the same base, x and x, you can add your exponents. This would turn into x to the 2 plus 5, which would equal x to the 7th. So if you look here, I have 2 to the first, 2 to the n minus 1. They both have the same base of 2. So we could turn this into 2 to the 1 plus the n minus 1, which would just be 2 to the n. So we can simplify this one to being 3n plus 1 all over 2 to the n. That's why that one might have came out a little weird for some of you guys that you might have stopped here, but this is simplifiable. Theo, does that answer your question? Labib, does that answer your question? Okay, good. Other questions? Yeah. In which one? 18, yes, it'd be the exact same thing that's going on in 18. Other questions? Yeah.
Is that also what happens
in number 8? That's exactly what happens in number 8. Yep. That's what I try to show. I kind of showed those steps where it's adding, but if you didn't understand the property, then yep, but it's the same thing in 8. It's also, if you look at 17, number 17, I gave you an answer, and I was okay with this one, 3 to the 1/3 to the n minus 1. I did tell you it is simplifiable. I said you can simplify it by using this power rule. Well, note 3 and 1/3 are not the same base. But you can use exponents to change 3 into 1/3 to the negative first power times 1/3 to the n minus 1 power. And so we could do that to create the same base. I'm good with this on a test. 3 to the 1/3. Don't worry about the power properties, especially if you're a little confused. Don't try something you're not sure of, because then you can lose points. I'm okay with just 3 times 1/3 to the n minus 1. I'm 100% fine with that on the test. I'm happy you just got the pattern, you understood it's geometric, and you went from there. All right, other questions on the homework? Let's ask more questions. As I was walking around, people had more questions. And ask it. Jacob, did I answer all your questions?
Yeah.
Okay. Who else was asking questions? Garv, I got to all yours. Okay. Then we'll say that we're good. Make sure you do not slouch on asking questions. I think 11.1D is one of the harder homeworks because you're not sure what's going on. You have to just try things, which makes it harder. When I tell you it's arithmetic, I'm going to use arithmetic. When I tell you it's geometric, I'll use geometric. When I tell you it's special cases, it just takes practice in understanding what's going on. All right, today we're going to talk about series and sigma notation. A series is basically a sequence, but rather than just taking that sequence, we're going to add all of the numbers together. All the numbers in a sequence are going to be added together. A series can come in 2 different types. The first type is called a finite series. A finite series could just be 1 plus 2 plus 3. Well, 1 plus 2 plus 3 would be a finite series. That would just equal 6. 6 is known as we'll get to that later. It'll be known as a partial sum because we're doing a part of a sequence. I guess I could put it on there. I was going to note it later. But that's called a partial sum. If we have a finite series or a sequence, we would have an infinite one as well. An infinite one of the same regard would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Don't put all those, just put a dot, dot, dot. This would be known as an infinite sum. Are we actually going to get this total? No, we aren't. But just a preface for in 2 days, there's going to be certain infinite sums that you can actually get the sum of. Those are ones that are convergent. When they converge on just one number, you can actually get that sum. It's a very special case. So in tradition, an infinite sum is you can't calculate it. But there's one case we'll learn in, I think, 2 days that you can actually come up with the sum. But for today, just go infinite sums, can't come up with a sum. Just put dot, 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 can't come up with a sum. All right, to tell someone we're doing a series, we're doing adding these things, we're going to use something called sigma notation so I don't have to list everything out that we're adding. Sigma notation will tell you are adding a whole bunch of numbers together. And we have some names that go along with this and why they're important. The first ones I want to point out to you are the 1 and the 6. Those are called your limits. So 1 and 6 are going to be your limits. Then let's look at that 3K. That 3K, all of it is called your summoned, which is kind of a cool word. You're summoned. That is just an explicit formula. And the last thing I want to point out is the K. The K can be any variable you want it to be, but the K is known as your index. Your index indicates what you're doing. Well, this is just a sequence that's being added. It tells you where to start and where to end, but you need to add it. So what's happening here is they're saying your very first number you should come up with is k equals 1. So we're going to take k equals 1 and we're going to plug it into that 3k. So this right here is going to be shorthand for what I'm about to show you. So it's shorthand for doing, let's go back to that black. So our equation is 3k. The first one we're going to plug in is 1. So we're going to have a 3 times 1. Then we're going to count up. I'm now going to add 3 times 2. My k value is going to become 2. Then I'm going to add 3 times 3. My k value is now 3. Then I have plus 3 times 4. My k value is 4. Plus 3 times 5. My k value is 5. Plus 3 times 6. My value is 6. And that's where you stop. This k equals 1 to 6 tells you to plug in 1, 2, 3, 4, 5, 6, and stop at 6. Tells you where to start, where to end. You have to count by 1. So it's always, wherever I start, we're counting by 1s until the next thing. So we should know from 1 to 6, there's actually 1, 2, 3, 4, 5, 6 terms. We will eventually need to know how many terms there are. The hard part about this is everyone says there's 5 terms. They see 1 to 6 is 5 terms. There are 5 steps, but there are 6 terms. 1, 2, 3, 4, 5 steps, but there are 1, 2, 3, 4, 5, 6 terms. So if I do 6 minus 1, that tells how many steps there are, but there is one more term than steps. All right, if I ask you to actually do this summation, what does that come out to? It comes out to 63. So, sigma 3k 1 to 6 equals 63. And then all that information I just said came down here. I did point out that these 2 letters need to match. You need to know what you're plugging in. You can't say this is X and this is Y, then technically you can't plug it. All right, let's do a couple examples. Write the following in expanded form. Expanded form means you're going to write it out, and you're actually going to do the addition if you can. So our first one is k equals 1, where k squared, all the way up to k equals 4. So we don't need to put it, but we should recognize that that is k equals 4 at the top there as well. So we plug in 1 for our k value, we come up with 1 squared. We plug in 2, we get 2 squared. We plug in 3, we get 3 squared. We plug in 4, we get 4 squared, and we stop there. Now we take out our calculator, or do it in our head if you want to. What is that sum? It is 30. You got it. So our actual answer would be 30. And just a reminder, that's called a partial sum. I am starting and stopping at a specific thing, so it's partial. I'm not going to infinity. That makes it a partial sum. Our next one would be called an infinite sum. An infinite sum because it tells you to go to infinity. So we would do 1 squared plus 2 squared plus 3 squared plus 4 squared. You can stop at any time. It'd be plus dot, dot, dot. Notational-wise, you should end with a plus and then a dot, 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 not just dot, dot, dot. So notationally-wise, you should have a plus and you should have a dot, dot, dot. I will say for math, I don't care. Put dot, 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 whatever. In math, if you're doing the dot, 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 the plus thing, the dot, dot, dot goes in the middle. If you're just doing 1, 2, 3, 4, 5, 6, the dot, dot, dot goes on the bottom of your equation. All right, next one. Not all indexes have to start at 1. You just have to start where they tell you to start. This one starts at 3. I go from 3 to 6. So I'm going to input 3, I'm going to input 4, I'm going to input 5, I'm going to input 6. I don't have a ton of room, so I'm going to go underneath. So we'll have 2 times 3 minus 1 plus 2 times 4 minus 1 plus 2 times 5 minus 1 plus 2 times 6 minus 1. Now I'd probably take out my calculator and plug all that in. What would this equal? Jacob? 26. Anyone else get 26? I'm not sure offhand. Okay, definitely not. Cool, let's go back. Theo, what did you get?
I got 32.
32. Did anyone else get 32? Okay, then we'll go with 32. Once again, that's a partial sum. Pay attention to this next one. If you don't know how to do this one, you don't know how to do this one. It's impossible to figure out. So I'm noting that we have I equals 1, but there is no I in here. You still have to have 5 terms. So just because there's no I in here doesn't mean that we don't have 5 terms. What it means is when I plug in my I value, it's not going to change my equation. I'm always going to have 4s. So when I'm looking at my first term, let's call it a sub 1. When I plug a 1 in here, there's no place to plug it in, so it doesn't change the 4. It just comes out as 4. When I plug in 2, I'm going to get out 4. When I get to my third term, I'm plugging in 4. When I get to my fourth term, I'm plugging in 4. When I get to my fifth term, I'm getting out 4. And I get a 5. And I stop there. So you have to know where to start and where to stop because you're not actually plugging in a number. It's just 4 plus 4 plus 4 plus 4 plus 4. In other words, it's 4 added 5 times, so it's 4 times 5, which would equal 20. This problem you cannot solve if you don't look back at this and understand what's going on. That you still have to add 4 however many times they tell you to do it. Common mistake on the test is someone just tells me it equals 4. Does not equal 4. It equals 4 plus 4 plus 4 plus 4 plus 4. So maybe put a star by that one. Make sure you study that one. It's a special case, and you can't figure it out without knowing how to do it. Yeah?
So if it's like I equals 2, would you do 4 times 2 plus 4 times 2? Or no?
4 times 2 plus 4 times 2.
Like if I equals 2.
Yeah. So we'd be here. We'd be starting on our second term, basically.
Oh,
yeah. So if I put I equals 2, we're basically starting at plugging in 2. So I would lose one of the 4s.
yeah.
Don't worry about changing up the formula. It's just, so you just, I think the easiest thing here is know how many terms you have.
Mm-hmm.
I have 5 terms. If we would have I equals 2, I would have 4 terms. We'd have to add it 4 times. If I had I equals, say, 3, I would have 3 terms. So we'd add 4 3 times. So you got to know how many times you're going to count 4. Yeah, that's a good question. That was a really good question. All right, what if we go the other way? So I give you a summation, you give me numbers out, and you add them. What if I go the other way? What if I give you numbers I'm adding, and I want you to come up with your sigma notation? Well, we're prepped for this. All this is coming up with an explicit formula. That is the hardest part about this. Come up with an explicit formula. So when I'm telling you to do 2 plus 4 plus 6 plus 8, what I want you to think about is the sequence 2, 4, 6, 8. And then I want you to come up with an explicit formula for that. Recognizing that 2, 4, 6, 8 is arithmetic because you are adding 2 over and over and over again. So that is arithmetic. Can someone tell me how to set up this equation if I have 2, 4, 6, 8, and I know it's arithmetic? Will?
So you would put, well, we start with k equals 1, and we use k. Or wait.
Don't worry about it. Don't worry about the summation. I just want to know what's the explicit formula for 2, 4, 6, 8. So a sub n equals.
A sub n equals, do I start with 2
Yep.
plus n minus 1 times 2?
Times 2. There you go. So first term is 2. Common difference is 2. We'd probably simplify that then. Well, that would be 2n. 2 times negative 1 is negative 2 plus 2 is 0. So it's 2n plus 0. You don't need the 0. It's just 2n. That should be the hardest part about your sigma notation. Now, for sigma notation, you can pick out any variable you want. Will, you talked about k. I'm just going to use n because I already have n up there. So we just have to make sure to put n equals 1 on the bottom. We're going to start out on our first term. And then we're going to go 2n. And now we just have to know where to stop. First term, second term, third term, fourth term. My 8 is my fourth term. So we're going to end at 4. Do not worry about where you start. You're always going to start at 1. If you are coming up with the equation, this is always going to be k equals 1, n equals 1, I equals 1, whatever. Something equals 1, and you count how many terms you have, and that's where you're going to put at the top. I have 4 terms, so I'm going to end at 4 terms. So let's look at the next one. I have 1, 2, 3, 4, 5 terms. So right off the bat, I know my Riemann sum, our summation. Our summation should go, let's make it k. We should go k, 2, 1, 2, 3, 4, 5. That's not going to change. This has to be true because I started on my first term and then on my fifth. Now all I have to do is I need to come up with an equation here. So I want you to start thinking about what is your index before you even begin. Because you can get on a test and mess this whole thing up, but at least you know this part, you'll get some points. This is probably the hardest one you'd have to do a Riemann, why do I keep going Riemann sum? A summation for. And that is because it is 1 over 5, negative 1 over 7, 1 over 9, negative 1 over 11, 1 over 13. So that is 1 over negative 7. So because Riemann sum is adding, I do have to make these negative. It is plus a negative. It is plus 1 over 9, so I have 1 over 9. It is plus a negative 111. And then finally it's a plus 1 over 13, and that's where it ends. Now what makes this the hardest one is this is not geometric. Yeah. It's an alternating arithmetic. So I need to have a negative 1 to an n, or a negative 1 to the n minus 1 to tackle this alternating stuff. So instead of worrying about the negatives, let's worry about that 5, 7. Let's go lighter. I'm just worried about this 5, 7, 9, 11, 13. Let's start with that, and let's just come up with a basic equation for that. How would I set up my arithmetic equation for 5, 7, 9, 11, 13? How would I set up that equation? Gar?
So an equals 5 plus n minus 1 times 2.
Times 2, because our common difference would be 2. I'm adding 2. 5 plus 2 is 7, 7 plus 2 is 9, 9 plus 2 is 11, 11 plus 2 is 13. Simplify that out a little bit, and we're going to have 2n plus 3. Now recognize, that's just our partial way. Jacob?
You have to add the alternating.
We have to add the alternating things. So what are we going to add in front? Is that going to be negative 1 to the n or n minus 1?
N minus 1.
N minus 1, let's check it.
Yes.
Okay. You're right. Don't second guess yourself. So if I plug a 1 in for this n, I'd have 1 minus 1, which is 0. Negative 1 to the 0th is positive 1. Is my first term positive? Yeah, you got it. All right, now don't forget about that this is a fraction. So we do have to put it 1 over that 2n plus 3. You can set this up slightly different. I'll accept either one of these. Either way is fine because that negative 1 really is just for alternating. You could throw that on top and make that negative 1 to the n minus 1 over 2n plus 3. You sure? Okay. But I will accept either one of these methods because we know it just alternates between positive and negative. It can go up front, it can go on top. It doesn't matter. All right, like I said, that's probably the hardest ones I'll throw at you for summation. Do we have questions on that one? Does that feel like something we could do? Possibly? And I'm like, meh, we'll see. Remember, locate things that are patterns. I see that 5, 7, 9, 11, 13 immediately. I didn't even look at the ones. I saw a pattern. All right, our next one. Our next one is not arithmetic. It is not geometric. Does anyone know what equation would work for this one? Yeah.
1 over n squared.
It'd be 1 over n squared. 100% correct. Because what I would notice is this pattern is 1 over 1. It'd be 1 over 4. It would be 1 over 9. It would be 1 over 16. So that means all of our denominators are n squared. My first term is 1, that's n squared. Second term is 2 squared. Third term is 3 squared. Fourth term is 4 squared. So we can jump right to our summation and go, well, that's 1 over n squared. Starting at n equals 1 and ending at, who knows? Put the infinity symbol on there. So we're going to tack on that infinity symbol because they didn't say just use those terms. That dot, dot, dot says use that infinity symbol. And we got our equation. All right, we tracking? Is it okay? Because we got, once you get it, it's super easy, but changing indexes can be very, very confusing, and that's what we're going to do next. So try to pay attention and ask questions if you got them. Like I said, it just takes practice. Once you get it, they're really, really easy. It's just understanding what I'm doing is the hard part. When you get to calculus, it's going to be important that you can actually change this index. So you have I equals 2. I equals 2 usually isn't that useful. Usually we want to reduce it to either 1 or 0. So what I want to do when we're changing indexes, we're usually changing this 2 to a 1, which is what it's going to say right here. It says rewrite the series with an index of k. So we're going to replace I with k. And we want to start at k equals 1. So let me show you what we're going to get to. We want at the end, I want k equals 1. But let's think about what that entails. If I want to be k equals 1, so we are going from, let's write this down. So I'm going from I equals 2 to I all the way to 6, and I need it to become k equals 1. So the first thing I'm going to notice is my index. My index, to go from 2 to 1, I am subtracting 1. Who wants to take a guess what happens to that 6? Who wants to take a guess at what happens to that 6? Be wrong. Who cares? Yeah. Not a 3. We're not. Yeah, 5. It'd become a 5. So if I'm subtracting 1, note, I think you're looking at dividing. We aren't dividing. We're going to subtract by 1. So if I take 6 and I subtract 1, we are going to have 5. So that's going to be 5, which makes sense. So think about how many terms are here. From 2 to 6, there are 4 steps, which means there's 5 terms. From 1 to 5, there's also 5 terms. When I add this up, these have to be equal to each other. So picture this summation. I need 2 plus 3 plus 4 plus 5 plus 6. I need this to also be 2 plus 3 plus 4 plus 5 plus 6. So let's talk about 2 ways. So we now need to change this. We can't just put k. If I just put k, let's see what happens. If I just put k. So remember what this is. This would be 2 plus 3 plus 4 plus 5 plus 6. Right now, this would be 1 plus 2 plus 3 plus 4 plus 5. Those are two completely different values. So we can't just replace I with k. We're going to go through the algebra of it, and then I'll tell you a way that I do it in my head. This is how I do it, and it goes really, really quick. So the algebra behind it is, well, if I start with I equals 2, I want to change that to k equals 1. So that's how the algebra works. Well, rather than think of this as k equals 2, what I want to do is I want to slowly introduce I into this equation. So I'm going to start with this 2. How does k relate to that 2? Well, we can't say k equals 2. That doesn't make sense. I said k equals 1. So instead of k equals 2, I'm going to go k equals 2 minus 1. What that allows me to do is I can now replace this 2 with I. So we would then have k equals I minus 1. If I add 1 to both sides, I'm going to realize that I just equals k plus 1. So anytime I see an I can replace it with k plus 1. So that means my new summation instead of I is going to be k plus 1. Now remember, this one was 2 plus 3 plus 4 plus 5 plus 6. This would now be 1 plus 1, which is 2. 2 plus 2, which is 3, 4, 5, 6. Both of these would be the exact same summation. Now, like I said, the algebra behind it, love it. A lot of people use it. But I'm going to talk about how I actually do it in my head. I think of it as being a lever type situation, or a balance beam, not a balance beam, but a scale. If I push down on one side of a scale, the other side comes up. So look what happened here. I am subtracting 1 from my index. So think of that as being lifting up on one side of the scale. That means the other side has to go down. So if I'm subtracting 1 from my index, I need to add 1 to my variable. So if I subtract from my index, I need to add to my variable. If I add to my index, then I need to subtract those values from my variable. So minus 1 here would be a plus 1 to my I. So minus 1 would mean this is k plus I. If this would have been minus 2, this would become k plus 2. If this was plus 1, this would become k minus 1. So that's how I do it in my head. Obviously, algebra way works out great as well. People use both methods. Let's do some examples. In both these examples, I do want to convert these to k equals 1. So in both of these examples, what I want is I want this to be the summation of k equals 1. Noting that to get to 1, I would subtract 2. So to get from infinity over here, I'd also have to subtract 2. Well, if you subtract 2 from infinity, you still have infinity. It does not change infinity. We do not write infinity minus 2. If you get out to infinity and subtract 2 from it, awesome, you're going to make a ton of money. You can't, so we're just going to leave it as infinity. All right, like I said, there's 2 ways to do this. We'll do the algebra way and we'll do the in your head way. In my head, I'm saying, okay, I'm subtracting 2 from my index. Subtract 2 means I'm going to add 2 to my variable. So instead of I'm going to have k plus 2. The minus 2 tells me I'm doing k plus 2. So in your head, you should have something that looks like this. 1 over, instead of I got k plus 2 squared. I added 2 to the I and replaced I with k. Now the algebra way of this, we should come up with the exact same answer, but I like to have 2 ways in case you get stuck on a test. We start with k equals 1. Then my goal is to rewrite this in terms of I. So the first thing I'm going to do is I'm going to take that 3 down and say k equals 3 minus 2. It still equals 1, but I use that 3. That's going to allow me to take that I and plug that in for that 3, which would give me k equals I minus 2. Add 2 to both sides, we should have had I equals k plus 2. Well, that's what we had. We replaced that I with k plus 2. Like I said, I don't care what method you use. This way is nice because I can now see your work. If you use kind of that scale method, maybe mention to me that you used it so I know what you're thinking when you replace it. All right, next one. We also want to go from I equals -1 to k equals a +1. So to get from -1 to a +1, you needed to add 2, which means to get from 5 to over here, I'm going to add 2. So we're going to go from 1 to 7 instead of -1 to 5. Okay, if I'm adding 2 to my index, I'm pushing down on the scale, the other side's going to come up. So instead of +2, I'm going to take away 2 from every single I variable. So I'm going to replace every single I variable with k minus 2 to account for this adding of 2, keeping everything balanced. So our end answer should end up being -1 to the k minus 2 over 2 times k minus 2. Let's use the algebra to support this. So the algebra starts with you going, okay, k equals 1. Now we want to start writing k in terms of I, so I'm going to pull that -1 down. So I'm going to go k does not equal -1, but it does equal -1 as long as I add 2 to it. Now I can pull that I and put it in place of that -1. And we can have k equals I plus 2. Subtract 2 on both sides. You're going to come up with I equals k minus 2. If you have room, you can simplify your answer. If you don't have room, that's fine. We did all the big work. But really, we should write this as 2k, what would that be, minus 3. Don't clutter your work if you don't have to.